Welcome to Web Handling. My name is Dave Roysum. In this module, we go beyond the basics of spreading to talk about traction and drives. This is necessary because some spreaders require traction. On the other hand, some spreaders can operate in traction or sliding, but do a better job in traction, while some can operate in either mode, but the application mechanics are completely different. Finally, some spreaders require sliding. Adding a drive motor is no less complicated because what the motor should be doing is not widely understood, even among drive suppliers. Also, what some drives are doing in practice is often the wrong thing. This module will help sort out the necessary details for best results spreading based on understanding the mechanics for each spreader type and mode. Before we begin with spreaders, we should first introduce or review the idea of forces acting in different directions. We will use a motorcycle going around a corner to illustrate the idea. Here we have two components. Gravity acts down and centripetal force acts outward while you're in a corner. Adding these vectors together gives the resultant of the tire pushing on the road. Of course, as Newton showed us, the road is pushing back on the tire in an equal and opposite direction. The second idea here is friction limiting physics. If the vehicle exceeds the available traction on a corner, it will slide out, with especially unpleasant results on a motorcycle. The maximum cornering speed can be calculated given the radius of the curve and the coefficient of friction between the tires and the road. Now, let's introduce the idea of a traction circle. Here we have a top view of a vehicle with four major directions that might compete for a part of the total traction. If we do not exceed the total traction, we are inside the green circle. If, on the other hand, we do exceed total traction, we are outside the circle and sliding. As a driver, we could choose to use 100% of the total for acceleration. Exceeding that would cause a burnout, as it is sometimes called. Alternatively, in an emergency, we might want to use 100% of the available traction for braking. If we are in a corner and going much faster than would be prudent, we might want to use 100% to hold the corner, whether it be a left or a right turn. What might be more to the point for the material to follow in the module is what happens if we want to accelerate or brake in a corner. Well, if we use part of the traction to accelerate or brake, we have less available to corner. That means we can't take as sharp of a corner if our foot is heavy on the gas pedal or brake. The same idea holds for webs. Here, instead of cornering, we will be looking at guiding or spreading. If we want 100% of the available traction to do spreading work, we don't want the drive to be also pushing or pulling on the web, nor do we want large bearings dragging or pulling on the web. So now let's put this learning to practical, everyday use. When in a corner, we do not want to put our foot on the brake. It is a deadly habit, whether on a motorcycle, in a race car, or even in your family car. The hand is safe only when it is on the throttle. However, zero throttle is not what we want. What we want is just enough throttle to tend to neither speed up nor slow down. In other words, just enough to counter drag. The principle is identical for helper drives that might be used for some rollers and some spreaders. Here, we don't want the drive to inadvertently change tension. Here, we don't want the drive to push or pull on the web at all. Here, what we want is the drive to just counter drag as well as inertia during speed changes. On a roller, this will keep the down web tension constant and steady. On a spreader, this will leave all of the available traction for spreading work. There are about a dozen spreader types that we discuss in great detail in Module 9 of my Web 101 class. We will not cover those essentials here. Instead, we will focus on details we often don't have time to discuss, namely details of traction and details of drive application. The concave roller is one of the simplest and best known of the spreader types. It is a roller whose ends are slightly larger in diameter than the middle. While this shape could be cut into an idler roller, it also can be made by applying a couple of wraps of masking tape where the edges of the web are running. Note that the web will be traveling slightly faster than the average at the ends and slightly slower in the middle in order to match the speed of the roller radii there. Of course, the speed difference and hence diameter difference must be tiny as shown by the starting point sizing equation given here. Now let's look in detail at the forces imposed by the roller onto the web as shown in this schematic. The tension profile, shown in red, is caused by the speed profile resulting from the diameter differences. Already mentioned, the ends are traveling faster than the average and thus pulls on the web as it enters the roller. The center of the web must then be slower, and thus the tendency toward compression. If the diameter difference is too great, this effect can overcome web tension at that center. The web could go slack there. Shown in green are the spreading forces acting outward. Finally, shown in black is the bearing drag that tends to slow all rollers, which in the case of a concave spreader is negligibly small. What is most important to note here is that we have forces acting in different directions. The tension profile acts in the machine direction, while the spreading profile acts in the cross direction. What you should have already anticipated is that we have two sets of forces at right angles that are both competing for the available total traction. This internal fight or competition for traction is one of the many reasons that this spreader is not as powerful as others. As we covered in Web 101, we can go from spreading to contraction merely by losing a bit of traction on the concave roller. Conversely, on the convex roller, we could go from contraction to spreading if we lost traction. This behavior is pretty binary. You tend to go from goodness to badness with little in between. This application and sizing and troubleshooting all require understanding the overall principles as well as the details, especially the details of forces and traction. The bowed roller, also known as a banana roll, Mount Hope roll, and curved axis roll, is also one of the common spreaders in the web industries. Unfortunately, common application does not mean common understanding. This spreader has one of the lengthiest and complex set of application demands in order to make it work well, or even work at all. Those details were already covered in Web 101. All we need to recall here is the mechanics of the spreader. Here, in the bowed roller mode, the mechanics are entirely determined by the normal entry law. Here, the ends must bend outward to meet the axis of the roller at a right angle. We also need to recall that the normal entry law is only valid in traction. If we break loose, it would begin at the ends first, because we are not asking anything of the center. The ends are where we are asking the web to get wider and to bend outward. However, the very edges are not usually where the biggest application problems are found. Rather, it is where the sliding outer portions meet the still tracking center. This results in what we sometimes call quarter-point spreading problems. This is easiest to see when trying to spread lanes after a slitter. The gaps in the lanes near the middle are large. On the other hand, the gaps between the end lanes may be non-existent. However, the quarter points don't just have no gap, they may be overlapped. The epidemic application error on the bowed roller that causes the previously mentioned problem is simply too much bow. As shown here, the amount of spreading increases with increasing bow magnitude. However, this only increases to a point. That is the point where traction begins to be lost on the ends. The proficient web handler should already be comfortable with the idea that a web could be in traction in one part of a roll, but not on another. The proficient web handler should know that slippage could not be measured or observed, but rather can be inferred by behavior, as was covered in Web 101. To avoid all of these problems, we must be very modest and very conservative with the amount of bow that we order. As given in the starting point table, the amount of bow that would be optimum may be less or far less than what you are accustomed to, especially if you do not come from paper mills where this is more common knowledge. You might not be able to rely on the bowed roller supplier or the machine builder in this regard, unfortunately, because many do not know this. Instead, the safest thing to do is to go to school yourself. There are many indicators that you have too much bow. A smile, frown, or M-shaped wrinkle profile is one. An easier indicator is if the spreader seems to operate better pointing into the sheet more than textbook along the path. What is likely here is that the spreader is acting in the bent pipe mode, operating in sliding as opposed to the bowed roller mode, operating in nearly complete traction. There are many other indicators of too much bow for the available traction that the especially attentive web handler might observe. Here, we will turn our attention to drive troubles that can cripple or totally disable the spreader. This may be a lack of a drive when one might be helpful or needed, or having a drive that's not properly tuned. To understand the friction limitations of the bowed roller spreader, we must know what forces the cover exerts on the web. The most obvious force would be the spreading forces acting outward in the cross direction. However, the bowed roller also has drag in the machine direction, just like any other roller. However, unlike other rollers, the bowed roller has more than two bearings. Instead, the bowed roller may have 24 bearings inside. Also, the flexing of the cover imposes even more drag on the web. Thus, never can drag be considered totally negligible. This is where drives might have an important role. If we needed to add a drive to overcome these drag forces, and if we could control that drive properly, both big ifs, we would let more of the available traction be used for spreading work rather than fighting the web in the machine direction. Ideally, we would tune the drive to match speed without a web by measuring torque at all speeds. During normal operation with a web, control torque to these measured values. The motor's torque would thus just counter the total drag of bearings and cover. There are more than a few complications with this ideal. The first is that the torque required to overcome drag is speed dependent and may vary with time and temperature, meaning you would need to have a curve or lookup table running inside the drive computer. Secondly, this drag will vary during the life of the spreader, but especially during the first few days of break-in. Thirdly, the torque control must be disabled on a web break. Fourthly, inertia compensation during speed changes need to be set up correctly. This ideal measured torque control is very different from common drive practice in which either speed is matched closely at one or two speeds or speed droop is enabled in the drive to prevent the drive from going into an overload condition. The overbowed or slippery bowed roller is just one of at least 4 variations of bent pipe spreading. All of these are running and sliding. Small exceptions might be the central section of the bowed roller and the quarter points of the hypercrowned roller that both might be running in traction. Much more complicated are dual spreaders, sometimes used to separate numerous lanes after slitting. Two versions use bowed rollers, but operate in totally different modes. In the tandem bowed roller mode, the bows are oriented along the path of the web as we discussed earlier. It is just that we are gaining the effects of more than one spreader. Because we are in the bowed roller mode, there are large traction needs. The more common is the dual bowed roller, where the bows are oriented in a very special and non-intuitive perpendicular direction. This folding spreader has only very modest traction needs and yet does some very powerful spreading. Finally, the least common is bowed pipes, as illustrated by the trademarked Posi spreader. This spreader operates yet again in a totally different mode and with totally different mechanics. However, it is easy to see, since these are bent pipes, that the spreader is in sliding. There are at least 3 design variations of the expander rollers. Here we show the most common, that is a set of elastic cords spanning between 2 cammed end plates. These cords are supported at several intermediate points or continuously. As the roller rotates, the cords stretch and thus drag against the supports. As you might already suspect, this roller has a lot of internal drag, and that translates to a large machine direction drag when the web powers this device. This spreader is nearly unique in that it operates well enough where a portion of the center might be in traction while most of the width is in sliding. Edge pull spreaders operate on the same principle as the bowed roller mode. Again, the normal entry law that is only valid in traction directs the edges of the web outward. The reason that this spreader can be so much more powerful than a bowed roller is because the edge pull rollers are nipped, and the nip provides a lot more traction capacity than a mere wrap angle would. In carpeting, these rollers may literally have teeth that grab into the backing. In the world of friction-limited spreaders, this spreader is close to the top. Tenter frames are a most powerful spreader used to maintain the width of heavy textiles or even permanently increase web width by many times during biaxial orientation. Here again, we grab a hold of the edges vigorously, in this case with pins or clamps. This spreader would be about as powerful as it gets because you will likely have enough traction to tear webs apart. Most of the spreaders we discussed earlier, when well designed and well applied, will apply an equal cross-direction spreading force at all points across the web. The spreading profile is then flat. Obviously, all bets are off, however, if we overbow a bowed roller as one example. However, the most powerful spreaders, such as the expander roller, edge pull rollers, and the tenter, all have inherently non-uniform spreading profiles. The profile is typically M or U shaped. Some of this profile comes from changes in traction profile across the width. Flattening is a less aggressive alternative to spreading that we discussed in great detail in Web 101. This mechanism requires either partial or whole-scale sliding. We have now at long last finished our tour of spreaders with a view to traction and drives. Here we summarize whether a spreader works best in traction or sliding, or both. Here we list whether a drive might be considered. Obviously, your mileage may vary as the saying goes. Still, understanding the mechanics and the details is often better than simply accepting common wisdom or accepting what was supplied by your builder, or by accepting mere guesses. Thank you so very much for allowing me to share my love of web handling. Let me know if you have any questions about this must-know topic or any other web handling topic.